Late August 1944, 6:15 hours. Observation post Phare, Pardal, France. The morning situation report lay crumpled on the desk as German officers of Flak Regiment 155W struggled to make sense of the numbers in front of them. The interception rates defied every calculation they had been taught in Luftwaffe technical schools across the Reich. 82% destroyed. The figure seemed impossible. Through their field telescopes, German observers had seen with their own eyes results that contradicted everything their intelligence services claimed about Allied air defenses. V-1 flying bombs launched in the pre-dawn hours toward London were being wiped out at a pace that no German mathematician could explain. These were not being shot down in risky chases by fighters. They were not colliding with barrage balloon cables. Instead, they were being blasted out of the sky by anti-aircraft fire over the coastal gunbelt. Shells were detonating right next to the missiles, exploding with precision that should have been impossible. At the headquarters of Flak Regiment 155W, located in the Château d'Eau West, Colonel Max Wachtel, commander of the entire V-1 offensive, received the reports with rising alarm. Over the course of the V-1 campaign, the percentage of missiles destroyed by coastal guns had jumped from 17% in June to 74% by late August. On one extraordinary day in the final week of August 1944, the figure climbed to 82%. It marked the beginning of the greatest technological shock German weapons scientists would face during the war. Neither Wachtel nor any German researcher understood that they were witnessing the secret use of one of the Allies' most closely guarded technologies, a device so revolutionary that it was protected at the same level as the Manhattan Project. The proximity fuse, coded by the Allies as the VT or variable time fuse, was quietly dismantling Hitler's so-called terror weapon with a level of accuracy German physics said could not exist. The story had begun 10 weeks earlier. On June 13, 1944, exactly 1 week after the D-Day landings, Hitler unleashed his long-promised Vergeltungswaffe, or vengeance weapon, against London. At 4:25 a.m. on that day, the very first V-1 crashed into Grove Road in Bow, destroying a railway bridge and nearby houses. 6 people were killed, 30 injured, and 200 left homeless. The weapon was the product of years of German research. A pilotless aircraft powered by an Argus AS-109-014 pulse jet engine, carrying 850 kilos of Amatol explosive at 640 km/h. It was the world's first operational cruise missile. German High Command believed it could force Britain to surrender. Major Walter Dornberger, leader of the V-weapons program at Peenemünde, had calculated that even with a conservative success rate of 25%, the V-1 would drop more explosive power on London than the entire Blitz of 1940-41. Each V-1 cost only 5,000 Reichsmarks to build, far cheaper than sending a manned bomber on a mission, and without the risk of losing air crews. At Peenemünde, German scientists were confident. They had already developed advanced rocketry, fielded operational jet fighters, and now deployed the first cruise missile. Dr. Robert Lusser, designer of the V-1's control system, insisted interception was nearly impossible. The missile's speed of 640 km, combined with altitudes between 600 and 2,700 meters, meant that only the fastest Allied aircraft, those exceeding 650 km/h, had a chance of catching it. To destroy one, a fighter had to close within 200 meters, putting itself at risk of being blown apart in the explosion. As for anti-aircraft fire, the odds seemed hopeless. German ballistic experts calculated that the chance of a direct hit on such a small and fast-moving target was less than 1 in 10,000 shells. This was not Nazi propaganda, but solid mathematical science. Conventional time-fused shells required prediction, calculation, manual fuse setting, and perfect timing. With the V-1 speed, gunners had at most 30 seconds from detection to firing. Colonel Max Wachtel, commanding Flak Regiment 155W, knew these challenges better than anyone. He had spent his career on both sides of anti-aircraft warfare. Between June and the end of the war, the Germans would launch 9,521 V-1s against England from ground sites, with thousands more fired at other targets. In total, about 25,000 V-1 missiles were deployed, but only days after the first launches, troubling intelligence reached German command. British defenses were adapting far faster than anyone predicted. By late June, interception rates had climbed to 24%. Higher than expected, but still within reason. Then July arrived, and the statistics no longer made sense. German officers tracking the effectiveness of V-1 attacks began noticing something strange. British anti-aircraft guns were reporting kill numbers that didn't match the amount of ammunition fired. From observation points along the French coast, they watched V-1 flying bombs cruising steadily toward England, only to be surrounded by bursts of flak and then tumble from the sky, even though the explosions had gone off too far away for a direct hit. What they were seeing, without realizing it, was the secret use of proximity fuses, devices that turned near misses into guaranteed kills. The technology had already been in combat in the Pacific. In January 1943, the cruiser USS Helena became the first ship to shoot down a Japanese dive bomber using shells that exploded automatically when close enough to the target, but German intelligence completely failed to recognize what was happening. This wasn't because they hadn't heard of it. The Oslo report from November 1939 had already mentioned research into proximity fuses, yet German scientists brushed it off as Allied disinformation. They themselves had tried to develop similar devices. Over 30 separate designs were studied, but none ever worked. The conclusion in Berlin was that such a weapon simply could not exist. The obstacles seemed overwhelming. How could anyone miniaturize radio transmitters and receivers small enough to fit inside artillery shells? How could fragile vacuum tubes survive the 20,000 G-forces created when a shell was fired? How could a battery be designed to remain inactive for years in storage but activate instantly once launched? For German scientists, the idea looked impossible. But by August 1944, American industry had solved every one of those problems. U.S. factories were producing 40,000 VT fuses every single day. During the final week of August, these weapons reached their peak effectiveness. The British had reorganized their entire air defense system to take full advantage of them. Anti-aircraft guns were now guided by American SCR-584 radar, which automatically tracked incoming V-1s. The shells they fired were tipped with VT fuses modified specifically to target the flying bombs. The Royal Artillery and RAF Regiment had even repositioned their guns, moving from the North Downs to the South Coast. This shift created a dense coastal gun belt, ensuring that any dud shells would fall harmlessly into the sea, away from German recovery teams. Once a V-1 crossed the English shoreline, it entered a carefully designed kill zone where radar and electronics worked together. The SCR-584 radar locked onto the missile, calculated its course, and fed firing instructions directly to the guns. Inside each shell was a miniature radio transmitter developed by companies like Sylvania Electric and Western Electric. When the returning signal indicated that the shell was close to the target, the circuitry, using ruggedized Therotron switches, triggered the detonator, sending fragments tearing into the V-1's thin hull. The results were devastating. On one peak day in late August, the coastal guns destroyed 82% of all incoming V-1s. For German engineers, such numbers were not just high, they were physically impossible. Reports of the 82% interception rate led to crisis meetings at German command centers. Colonel Max Wachtel even suspected sabotage. Emergency checks were carried out on the missiles, but no defects were found. Test firings over German territory showed that the V-1s performed exactly as designed. The problem appeared only when they faced British defenses. With no clear answers, German experts could only assume that Britain had developed some revolutionary new anti-aircraft system. Yet they had no idea what it was. They tried every countermeasure, launching at different altitudes, firing larger salvos, sending night attacks, even using weather conditions to mask the missiles. Nothing worked. The kill rate stayed catastrophic. At Peenemünde, German scientists were forced to consider the unthinkable. The Allies may have achieved what they themselves had dismissed as impossible. If the British and Americans had truly built functioning proximity fuses, then the technological gap was beyond repair. But uncovering the secret proved impossible. Allied security around the program was airtight. Production of the fuse was split across 110 different factories. Workers only knew their small piece of the process, never the whole. Even the name variable time was a deliberate deception, making it sound like just another type of timed fuse rather than a proximity sensor. By 1944, the American electronics industry had been almost entirely redirected to fuse production. By the end of the war, The United States had built 22 million proximity fuses at a cost of more than $1 billion in 1940s money. One company, the Crosley Corporation, manufactured over 5 million of them, nearly 1/4 of the total. The scale of production exposed the sheer industrial mismatch. While Germany was still building V-1s with forced labor under constant bombing, the United States had turned consumer radio and electronics companies into war factories capable of churning out advanced weapons by the tens of thousands. At its peak, daily American fuse production reached 40,000 units. Costs had plummeted as well, from $730 per fuse in 1942 to just $18 by 1945. Crosley, which before the war had made radios and refrigerators, now employed 10,000 workers who produced 16,000 fuses a day at peak output. Sylvania Electric dedicated its entire vacuum tube division to the program, developing hardened, miniaturized tubes by the hundreds of thousands, 400,000 every day. By 1945, 95% of all tubes used in the program came from them. The contrast between the two sides could not have been sharper. Germany was handcrafting advanced weapons in limited numbers, while America was mass-producing revolutionary technology on a scale the world had never seen. By late 1944, monthly U.S. proximity fuse production alone was greater than the total number of V-1s Germany had managed to launch during the entire war. The proximity fuse was one of the most advanced pieces of engineering of the Second World War. To work, it had to survive incredible stresses, being fired from a gun barrel, withstanding 20,000 g of acceleration, spinning at 25,000 revolutions per minute, and enduring extreme temperatures. Sylvania engineers solved the problem by developing miniature vacuum tubes originally based on hearing aid designs, but reinforced to survive the violent forces of firing. The fuse carried batteries that could remain inactive for years in storage, yet activate instantly once the shell was launched. Inside, a miniature radio constantly transmitted signals. When those signals bounced back from a nearby object, the circuits triggered detonation. The idea sounded straightforward, but each part required overcoming obstacles German scientists had declared impossible. Quality standards were unlike anything seen before. Every single fuse went through multiple layers of testing. Random samples were even fired from test guns to make sure they functioned in combat conditions. The rejection rate stayed below 2%, a remarkable achievement for such a complex device produced in massive numbers. By September 1944, the effect was clear. The V-1 campaign had been broken. Of the 9,521 V-1 flying bombs launched from ground sites against Britain, only 2,515 reached London. The attacks killed 6,184 civilians and injured 17,981. The toll was heavy, but it was far below what the Germans had intended. General Frederick Pyle, commander of Britain's anti-aircraft command, later calculated that without proximity fuses, the casualties in London would have been 4 to 5 times greater. The fuse quite literally saved the city from destruction. In desperation, Germany shifted to night launches and introduced the V-2 rocket, which flew too fast for interception. But these changes could not alter the overall outcome. The V-1 turned into a costly failure, consuming resources that Germany badly needed elsewhere. The German inability to identify the proximity fuse became one of the greatest intelligence failures of the war. Despite having vast spy networks and brilliant scientists, they never figured out what was destroying their weapons. Not a single intact fuse fell into German hands during the entire V-1 campaign. An almost unbelievable moment came during the Battle of the Bulge, when German troops captured an American ammunition dump containing proximity-fused shells. They looked at them but dismissed them as conventional timed ammunition. Their assumption that such technology was impossible blinded them to the truth even when it was in their possession. After Germany's surrender, interrogations confirmed their ignorance. Colonel Max Wachtel told Allied officers that German command believed the British had improved radar or faster mechanical fuses, but they never imagined self-triggering shells. When German scientists were finally shown captured American VT fuses, many refused to believe what they were seeing. They could not understand how vacuum tubes could survive the shock of firing, how batteries could last for years, or how circuits could remain functional after being shot from a gun. They admitted they were at least 10 years behind American technology. Dr. Merle Tuve, who directed fuse development at the Johns Hopkins Applied Physics Laboratory, later explained that the key was cooperation. Scientists, engineers, and factory workers worked together in a system that encouraged innovation and problem-solving. In contrast, Germany's rigid authoritarian structure stifled that kind of collaboration. The proximity fuse proved that the outcome of World War II was shaped as much by laboratories and factories as by soldiers on the battlefield. While Germany poured resources into exotic wonder weapons, the United States focused on technologies that multiplied the power of existing systems. The proximity fuse made every anti-aircraft gun between 5 and 10 times more effective. Secretary of the Navy James Forrestal summed up its importance. The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater. The V-1 program itself relied heavily on slave labor. Tens of thousands of concentration camp prisoners were forced to work in underground factories, and many died under horrific conditions building the missiles. By contrast, American workers willingly put in long hours, often for extra wages, never knowing exactly what they were making, but aware that it mattered for the war effort. At Sylvania's Ipswich facility, more than 5,000 women worked 12-hour shifts producing critical components. It wasn't until after the war that they learned their labor had helped save London from destruction. The secret of the proximity fuse remained so tightly held that even British anti-aircraft crews using it in battle were not told how it worked. They were simply issued special ammunition under strict accounting rules. Every shell had to be tracked. Any unexploded rounds were immediately recovered. Naval patrols even guarded the channel to prevent German forces from retrieving duds. The Allies managed to keep the proximity fuse completely secure until the war's end, a technological triumph that helped decide the outcome of the conflict. The secrecy surrounding the proximity fuse came at a cost. Allied ground forces were not allowed to use it in artillery until December 1944. Thousands of soldiers lost their lives in Europe because the device was considered too valuable to risk falling into German hands. Even so, its use against the V-1 flying bombs was judged essential. London's survival during the invasion of Europe was critical to the success of the Allied campaign. For Germany, the V-1 program drained massive resources while achieving very little. In total, about 25,000 V-1s were launched. The program cost millions of Reichsmarks and tied up factories, workers, and materials that could have been used for fighter aircraft or anti-tank weapons desperately needed on the collapsing fronts. There was also a moral failure. The V-1 was produced largely with slave labor. Tens of thousands of concentration camp prisoners died in underground factories building these weapons. In contrast, the proximity fuse was defeating those same missiles, and it was made by free American workers, many of them women, who labored voluntarily in long shifts without even knowing what they were building. Only after the war did they learn that their work had saved London. The proximity fuse was more than a weapon. It marked a turning point in the very nature of warfare. It showed that victory came not from a single superweapon, but from engineering, production, and mass deployment. Modern war had become a contest of industrial systems, not just military units. Before it protected the Pacific Fleet and helped drive Japan to defeat, the fuse saved London. The German officers watching V-1s explode in midair never understood why it was happening. Within their scientific framework, the technology seemed impossible. The transformation was dramatic. Before the fuse, bringing down a single V-1 required an average of 2,500 heavy anti-aircraft shells. With proximity fuses, the number dropped to about 100. In just 10 weeks, interception rates jumped from 17% to 82%. This was not due to bravery or training, but because of advanced electronics produced in massive numbers, something Germany could not match. The United States had mobilized its entire electronics industry. Over 80,000 workers were employed, and more than $1 billion was invested to produce 22 million fuses. The War Department declassified the weapon in September 1945. Its announcement described it as one of the most important weapons developed during the war, surpassed in effectiveness only by the atomic bomb. For German scientists, the revelation was both clarifying and humiliating. They finally understood why their V-1 campaign had failed, and it was not because of bad design or poor strategy. They had been beaten by industrial capacity they never imagined possible. They had believed the V-1 represented the peak of weapons technology, To learn it had been countered by small mass-produced devices costing less than $20 each was devastating. They realized they had not been defeated by soldiers in the field, but by the production lines of Allied industry. The proximity fuse did not disappear after the war. Its principles evolved into modern air defense systems, radar altimeters, and electronic warfare. For many of Germany's former weapons scientists, it remained a permanent reminder of how far behind they had fallen. The lesson was clear. In modern war, producing good technology in huge numbers is far more decisive than crafting a handful of perfect weapons. Germany created brilliant individual machines, but America built effective weapons by the millions. On that extraordinary day in late August 1944, when proximity fuses destroyed 82% of all incoming V-1s, warfare itself changed. German crews launching their vengeance weapons never knew what was defeating them. They had done everything right by their own standards, designing advanced machines, training skilled operators, achieving genuine breakthroughs. Yet they were brought down by mass-produced electronics they could not even imagine. The proximity fuse saved London through thousands of controlled explosions, each one guided by a piece of technology German experts had sworn was impossible. It was proof that industrial democracy, with its ability to mobilize free workers, could outperform totalitarian engineering that relied on forced labor. It was the triumph of large-scale production over handcrafted perfection, of simple solutions multiplied millions of times over exotic wonder weapons. The Germans never discovered what was destroying their V-1s as they crashed burning into the ground. They had been beaten by a secret they did not understand, and by an industrial strength they could never equal. In the end, Hitler's vengeance weapon became London's salvation. America's true victory was not only on the battlefield but also in the factories, where millions of workers, many of them women, built tiny electronic devices that changed the course of the war. The 82% interception rate achieved in late August 1944 proved a final truth. In modern warfare, industrial capacity can defeat any so-called wonder weapon. The proximity fuse was more than a tool of war. It was living proof that the combined force of science, industry, and free labor could overcome tyranny. And the Germans, watching their V-1s fall from the sky, never realized that they had already lost long before the battle was over.